All right, welcome to my online class. So today's lesson or topic is about the relative velocity. Then I will be explaining relative velocity with the aid of the videos and the pictures. Right, as you can see here on the screen, the relative velocity is the velocity an object appears to have when seen by an observer who may be stationary or moving. Or someone can say a relative velocity is about how fast something appears to be moving compared to something else. Relative velocity is about how fast something appears to be moving compared to something else. So this velocity actually depends on the perspective of the observer. Okay, to get what I'm talking about, let's go to videos. Right, I have two trains here. There is this one that you can see the seat of, then there is this other one there. So now maybe let me ask you the question. So between these two trains, I want to know which one is in motion. So let's say this one is train A, this one is train B. So I'm going to play the video here. So once the video starts playing, you will see there will be movement. So I'll want to know which one is actually moving between the two. Yeah, I can see some movement there. Let me repeat it again. Remember, I've asked that which one is moving between train A and B. Yeah, so for someone who'll be inside this train or for someone who'll be sitting on this seat, his eyes will show him that the train B is the one in motion, while actually the train is that is in motion is the one is train A. So you will see that just now. So me and you right now, in our perspective, it will appear that train B is the one moving and then is moving to the right. That's what I'm seeing right now in my perspective. So that is what is going to be seen by someone sitting on this sofa, on this seat here. Okay, let this video continue. So as it continues, you will see that actually the train in motion is train A. Is train A. So train A is the one which is in motion. Then train B is stationary. So as I've said, we've said that relative velocity is what appears uh, for the eyes of the observer. So in this case, we're going to say that train B or the ground or the buildings. So let's see, check the ground and the buildings and the trees. When you check the grounds and the buildings and the trees, they appear to be moving. So they appear to be moving to the right hand side. So in this case, the trees and the train B will have what you call the relative velocity. So we're going to say that these things, they are in motion relative to the someone in train A. So someone in train A, when he looks at the tree, those trees appears to be moving to the right. Therefore, we're going to say that the velocity of the tree relative to the observer inside train A is blah 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 blah. Maybe it's 5 meters per second. So we're not going to say that the speed of the ground or tree is zero. No. Yes, it's zero, but it depends on the perspective. So in this case, in the perspective of someone who's inside the train A, it will appear that those trees are moving at a certain speed. So therefore, this tree will have a relative velocity. Right. Here I'm just emphasizing what I've been saying. If you are moving, when you look at the ground or the trees, it will appear that those trees are the ones in motion, and then yourself, you will feel like you are not moving at all. You will feel like you are not moving, and then what is moving are those trees and the tar road. So that's what we're seeing here. Therefore, in this case, we're going to say the trees are having the relative velocity. Therefore, the velocity of the ground won't be the relative velocity of the ground won't be zero, because when this guy looks at the tar road, it appears that the tar road is moving at a certain speed. So we're going to give the tar road a certain speed, and then that speed of the tar road will always be equal to the speed of this vehicle. It's just that the tar road will move in opposite direction. So if this vehicle is going forward, then the tar road will move with the same speed in opposite direction. Right, here we're having two trains moving in opposite directions. So this guy that you see there inside that train, we're going to call him the observer. So that guy there's observing this other train. So this guy and the train that he is in it, they're moving at the speed of 30. The other train is moving at the speed of 60. Therefore, when this guy that you saw there looks at that other train or observes that other train, to him it will show that this train, which is moving with the actual speed of 60, it will show that that train is moving actually faster than the real speed. So to him, or his eyes will show that the train is moving faster than the actual speed. So this train is moving with the speed of 60 kilometer per hour, but because that guy that you saw there is moving, because that guy is also in motion and this other train is also in motion, so it will appear that this other train is moving faster than the actual speed. Okay, let me show you something to make sense of that. So once you have two objects in motion, uh, when there's someone observes the other object, if I'm in a car A which is in motion and I observe car B which is in motion, and then those vehicles are moving in opposite direction. So the other vehicle will appear moving faster than its actual speed. Let's see here. Uh, Okay, uh, you will observe the the relative velocity of the trees. Look at the trees at the moment. So the trees appears to be moving to the right, but they appear to be moving slower. Then once this train comes in, you will see that uh, the speed, the passing speed, it's now faster. Let me let's observe that. So look at these trees. They are moving backward, but at a lower speed. But look at now here. So you see this other train moving very, very, very fast. Fast, 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 passing like that. So that is a very, very fast speed. So what's happening here is that if this train is moving at the speed of 100 kilometer per hour, these trees will appear moving in that direction, which is opposite to the motion to the direction of this train. So the trees will appear moving backward with the same speed. So in this case, if we have uh, two objects moving in opposite direction, to get the relative velocity, you'll just have to add uh, the speed of the movement. Let me just write it. Yeah. So okay, for now we're dealing with different direction. Why is a different color now? Let me use white. Okay. I'm saying opposite direction. You, you add the speed to find uh, you add the velocity to find the relative velocity. Okay, let me write it in full at velocities. Velocity. Okay. Relative velocity. So that's why I said that in this case, the relative velocity of the tree with respect to someone inside this train is going to be 100, which is the speed of the train, plus 0, which is the actual speed of the trees. Then we'll have 100. So what is the meaning of this is that okay, well, normally we're going to write this like this. We're going to say relative velocity of the trees with respect to the train. I'm going to have same subscript now, tree and train. Let me call this train a locomotive. Let me use L. So we say the relative velocity of the tree relative to the locomotive. So in other words, we are trying to say that the velocity of this tree in the perspective of someone in the locomotive is 100. And then direction will be east, meaning that someone in this locomotive, when he observes or she observes these trees here, it will appear that these trees are moving to the east with the speed of 100 kilometer per hour. Right, so we're done with that. Now let's continue. As I've said, the relative velocity now for the trees will be 100. So that's why you're going to see slower movement. So when the train now comes, you will see that the train is moving faster than the trees. You can even see those trees at the top. Those trees, they are moving a bit slower, but they're also moving to the east, but a bit slower compared to the train. So that's what will appear to the eyes of the observer who is in this locomotive. He's going to see this train moving faster. So actually what will be happening here is that let's say we're going to say that the velocity of that train, so this T now doesn't stand the tree, it stands for the train, relative to the locomotive. So since these two uh, objects in consideration, they're moving in opposite direction, we're going to apply the very same thing, opposite direction, and add the velocities to get the relative velocity. Therefore, we're going to say that the velocity of locomotive plus the velocity of that train. So let's assume that both train and the locomotive are moving with the speed of 100 kilometer per hour. So this one is moving 100 kilometer per hour, this one 100 kilometer per hour, but in opposite direction. So when you get them, add them, you'll get 200 kilometer per hour. Therefore, what is the meaning of this? It means that the velocity of the train which is this train, relative to the locomotive, which is this one here, is 200 kilometer per hour. So in other words, it means that when someone is inside this train L, when the observer is in this train L, someone who's in train L, when he observes or looks at this other train, it will appear that this train is moving with the speed of 200 kilometer per hour towards east. So while in reality this train is not moving with the speed of 200, but is moving with 100 kilometer per hour. So in other words, this train will appear moving faster than its actual speed. So that is what we saw in that first scenario where the train was moving with 30, the other one was moving with the speed of 60. But when that other guy observes that other train, it appeared that that other train is moving with the speed of 90 kilometers per hour. So when we've got two objects moving in opposite direction, when one of the observers from either of these trains, when he looks at the other train, it will appear that the other train is moving faster than its actual speed. So normally this second letter here, so this second letter here, it represents or it gives us the position of the observer. So always this second letter here represents the position of the observer, meaning that someone in locomotive L is looking at this train T. Then when this observer is looking at train T, it appears that train T is moving with the speed of 200 kilometers per hour. So that's what we've observed from this video. So for the last time, the trees are moving slower, 100, then this train is moving fast now, passing fast quickly. So it appears to be moving at the speed of 200 kilometers per hour. Right, now we're changing the perspective. So now the observer is no longer in this train, but the observer is on the floor. So this guy on the floor is looking at these two trains at the same time. So now, because this guy is not moving, is static, this guy can say is on the ground. So someone on the ground will see things as they are. So if this train is moving with the speed of 30, that's what will appear to the eyes of this guy. This guy will see this train moving with the speed of 30. So this other one is moving with the speed of 60. This guy will see this train moving with the speed of 60. So there is no way he will see that other train moving with the speed of 90. So the reason initially that other guy saw this train moving with the speed of 90 is because the observer was in motion. So this time the observer is not in motion, therefore is going to see this train moving with 30 and then this one with 60 because he is stationary, he is not moving. So now let's go to a different uh, perspective. Right, here is another scenario where you'll have two trains moving in the same direction, same speed. So what's going to happen now? The observer is in this train, this first one here, then he's looking at that other train. So now let's see what he's going to see. This is what he's going to see. So when you observe that other train, it will look like that other train is not moving at all. Therefore, in that case, we are going to say that the relative velocity of that other train, it's zero. So why? Because it will appear as if that other train is not moving in the perspective of this guy. So this is what this guy is going to see. It seems like there is no movement at all. So it takes us back to that thing that I've said that uh, where to write it. Let me play the video again. I want to write something. Yeah, let me stop it and write here. Yeah. Okay, same direction. Sub, subtract. Oh, yeah, not sure of the spelling. Subtract, subtract, subtract. It's S there. Subtract velocities. Forget relative velocity. Right, there is no S here. Yeah, subtract velocities to get the relative velocity. So that's why this other train will appear as if it's not moving. It's because of that you are going to say relative velocity will be equals to the velocity of this train. Let's say it's moving with the speed of 60 minus the velocity of this train as well. The speed is the same. Remember, in this case, we've got same direction and same speed. So 60 minus 60 will be 0. So in this case, there is no relative velocity, meaning that from the perspective of the observer, someone who's in this train, when he looks at that other train, it will appear that that other train is stationary. That's what this guy is going to see. But when we change the perspective, someone on the floor is not going to see that other train stationary. He's going to see that other train moving. As you can see, this guy on the floor, he will To him, it will appear that those trains, both of them, they are in motion. Right, let's go to a different scenario now. Yeah, now, so let's go to a different scenario again. Suppose you are driving a car and you overtake or you approach the other car from behind, and then that car that you are approaching, it's moving at the slower speed compared to yours. So what will happen is that the driver or the passenger from the car behind, that passenger or the driver from the car behind will see the car coming backward, or immediately when you pass that slow car, it will appear that that car is moving backward. So in that way, we're going to say that relatively that car is moving backward, even though that uh, both cars, they are moving forward. It's just that one of the vehicle is moving slow, then the other one is moving faster. But in the perspective of the guy who will be on the faster vehicle, which is going to overtake the other vehicle, in the perspective of that guy, it will show that the other slower car would be moving backward. So that backward movement, which is velocity, is what we call the relative velocity. Uh, let's see that from this video here. Yes, the slower car, yes, the red car passing. So look at this box here. Look at this box. Right, even though it's not exactly the same scenario, but it's similar thing. So I hope you've seen that, but let me repeat it again. Yeah, so this car is moving fast. This one is slow or it's static. So look at this mirror. That's what we're going to see. It will appear that this blue car is moving backward. So even though it's not moving backward, it's just moving slow or it's static. So let's have a look again. Yeah, let's start somewhere here. Look, the red, someone is in this red car observing this blue car. So when you observe that blue car, it will appear that that blue car is moving backward. So that is the view of someone inside that car. So let's see. It's not the scenario that I'm talking about. Yeah, here's the scenario that I'm talking about. The first car is coming, a red car. When the red car looks at the blue car appears to be moving backward. Hopefully you've seen that. Here again, that's what the blue car will appear moving. So the blue car will appear moving backward. Even though that this blue car is not moving backward, it's just stationary or is moving forward with the lower speed. So back to what I've started. Remember what I said before, and I also wrote it. Same direction, which is what we've seen. These two vehicles are going in the same direction, but with different speed. Okay, I said that same direction. To get the relative velocity of two vehicles in same direction, you are going to subtract. You are going to subtract. And then whether you subtract 80 from 100 or 100 from 80, it depends uh, on the position of the observer. It depends who is looking which car. So we've got two cars. Who is looking or who is observing? Is the driver of the red car observing the blue one, or is the driver of the blue one observing the red car? But from our scenario, we've been saying that the red car is the first one is moving from behind at a higher speed. Then when the driver of the red car observes the blue one, it will appear that the blue one is moving backward. Therefore, in this scenario, the observer will be in the red car. Then if the observer is in the red car, then you will start with the speed of the blue car minus the speed of the red car. Remember, same direction, you subtract the velocities. So as I've said that if this is the observer, the red car, then the relative velocity, you start with the speed of this, which is 80 minus 100, which is going to be negative 20 maybe kilometer per hour. So what is the meaning of this negative? The meaning of this negative, it means that this guy who is moving faster, when he looks at this blue car will appear moving with the speed of 20 kilometer backward. So the blue car will appear moving backward with the speed of 20 kilometer per hour. And then if the observer is this one from this car, then the relative velocity will be, you'll start with this. You'll say 100 minus 80, then you'll get positive 20. Then positive means this direction. Then it means that when this guy driving at 80, when this guy observes this vehicle, this guy of the blue car will see this red car moving forward with the speed of 20 kilometer per hour. Right. Right. Now let's go to a real life scenario. We're going to have two vehicles. One of the vehicles is the truck. Here's the truck. This truck is moving with the speed of 100 kilometer per hour. Then there is this car, which is the car of the cameraman. Cameraman is in this car. So this car is moving forward with the speed of 95 kilometer per hour. So they're all going in this direction. Then I said that same direction relative velocity will be equals to the difference of these two velocities, which is going to be 5. So now I've said that whether you're going to say 100 minus 95 or 95 minus 100, you have to know who is the observer. In this case, the observer is going to be the cameraman. So if the observer is the cameraman, which is the view that we're going to see, then we're going to start with 100 minus the speed of the observer. So we always subtract the speed. We start with the speed of the object that we're looking for, and then we minus with the speed of the observer. Then we're going to get positive 5. So what is the meaning of this positive 5? Positive means this direction. So it means that when the cameraman observes this car, it will appear that this truck is moving forward with the speed of 5 kilometers per hour. Remember, the actual speed of this truck is 100, but because the cameraman is also moving, then it will appear that that truck is moving at a lower speed compared to its actual speed. But I will just play the video now. You will see that. Here we go. That truck is moving with the speed of 100 kilometers per hour. But because this cameraman is also moving, that's why you don't see that truck as if it's moving fast. It appears that that truck is moving with the speed of 5 kilometers per hour going forward. So you can see this truck, if you want to see that 5 kilometers per hour nicely, look at the passing rate. Look at the passing rate. So this car will be passing the cameraman but slowly. So it's going to pass the cameraman with the speed of 5 kilometers per hour. So here we go, here we go. The cameraman and the truck, can say they're almost still in line. But as the time goes on, the truck after some time it will be forward. It will be forward. So right now it's still passing. It didn't pass the cameraman. It's still passing, but it's passing slowly. So it's passing forward with the speed of 5 kilometers per hour. All right, the previous problems that I've discussed so far, we're calling them the parallel move. Let me say motion. I can't write properly parallel motion problems. I'm talking about the problems that the previous problems that I've discussed so far. You remember you had a scenario where a train is moving like this, the other vehicle moving like this. So this movement is parallel to this, or the two vehicles were moving in the same direction like this. So this line is parallel to this. So now we're going to have a different scenario where you will have one of the object is moving like this, and then the other one is moving like this, or one of the object is moving like this, then the other one is moving at an angle like that. So it can be any kind of motion like this and like this. So as you can see, these lines are not parallel. So this line here is not parallel to this one is not parallel to this one is not parallel to. So this kind of problems we call them non-parallel problems. So to solve this kind of problems, we can use the method called the components method, or we can use sine rule and cosine rule, or we can use the right angle triangle theorem, which is where you will be using Pythagoras theorem and the trigonometric ratio. So you'll have about three options. Yeah, so please let's listen to this guy here. Is explaining nicely. Let's listen to him. I think I won't have to repeat what he will be saying because Akotin Timui explains very well. Let's listen to him.
Then please go back and watch those videos and then come back over here, because in these videos we're gonna talk about relative velocities between things that are moving at some angle with respect to each other. So let's take an example. So imagine we have a situation where a sheep and a lion are moving perpendicular to each other on streets. Yeah, they're animals running on the street. What we would be interested now is in calculating the relative velocities in this example. Like, for example, what is the velocity of the sheep as seen by the lion from the lion's perspective? What would that be, and how do we even calculate that? Could we just like directly subtract? Can we do that? Well, let's see. What we can do is we can use the same concept that we did before. The concept was this: if you want to calculate from velocity of the sheep from lion's perspective, then we have to look at things from lion's perspective. The first thing is the lion does not see itself moving. As far as the lion is concerned, it's at rest. And this is familiar. And when you're jogging, you don't see yourself moving, right? Instead, you would see the rest of the world going backwards. Similarly, over here, lion would consider itself to be at rest, and the whole world, including this road, would be going backwards at 3 meters per second. All right, so let's just look at what that looks like. So here it is. Let's jump into the lion's reference frame or lion's perspective, and from the lion's perspective, you would see the whole road going backwards this way. And if you've used GPS, then you see something very similar, right? You don't see yourself moving, you see the rest of the world moving. Now comes the big question. What will the lion see the sheep doing? I mean, think about it. The sheep is moving 4 meters per second on the road, on the ground, but the ground itself is traveling backwards 3 meters per second. So to figure out the relative velocity of the sheep, seen from the lion's point of view, we will wait for 1 second and figure out where sheep ends up. All right, let's do that. So in 1 second, we would see that the sheep would have traveled 4 meters on the ground. All right, so let's just write that down. On the ground, the sheep would have traveled 4 meters. Here it is, 4 meters on the ground per second. But in that 1 second, you would also see that the road and the sheep would have gone downwards 3 meters. Okay, so let's put that in as well. So the road and the whole ground, whole ground goes 3 meters in 1 second. So now here comes the big question. How much did the sheep move? Well, notice the sheep was initially over here, but now it's over here. So if you look from the lion's point of view, the sheep has moved in this direction, this way. So this means that the sheep is no longer traveling towards the right. Instead, the lion would see the sheep moving this way, this direction. That is the direction of the velocity of the sheep. And at first it might sound a little weird as to, why would the sheep be doing that? But let's play an animation to really convince you that that's really what's happening. So here it is. Here's the perspective of lion. All right. This is not very convincing, isn't it? Okay, let's look at it one more time. This time we will see some ghost images. You can clearly see now that the sheep is indeed moving at an angle, isn't it? So watch it over and over again until you really get convinced about this. All right. Okay, now the next thing would be to calculate this. How much is this distance? Well, this is a right angle triangle. And in right angle triangle, we can use the Pythagoras theorem. This is our hypotenuse. So we could say the hypotenuse squared. The Pythagoras theorem says the hypotenuse squared is equal to the sum of the squares of the other two sides. So that should be equal to the square, 4 squared, plus 3 squared. And that gives us 16 plus 9, which is 25. Or the hypotenuse turns out to be the square root of 25, which is just 5. Which means this length is 5 meters, and this happened in 1 second, right? So we could say it's 5 meters per second. This means that the lion sees the sheep traveling 5 meters this way in 1 second. In other words, the relative velocity of the sheep, as seen from the lion's perspective, is 5 meters per second this way. Alright, now since we're talking about velocity, it's not just the magnitude, we also want to calculate the direction. I mean, no, we understand the direction is this way, but what exactly is this direction? So we can answer that by calculating the angle. So let's calculate this angle, for example. How much is this angle? So we can use trigonometry. We can use sine, cos. We usually prefer to use tan. It's not a necessity. You can use anything you want. But if I use tan, we will get the opposite side. 3. Oops, let's put the proper colors. 3 divided by 4. That makes theta equals tan inverse of 3 divided by 4. And there we have it. So if someone asks you now what's the relative velocity of the sheep as seen by the lion, we could just say it's 5 meters per second at an angle of tan inverse of 3 by 4 with the horizontal or something like that. Alright, now let's put the whole thing, this whole result, in terms of symbols. Okay, remember how we used to write symbols for relative velocity? Well, we are calculating velocity of the sheep with respect to lion, right? So we would write it as velocity of the sheep with respect to the lion. The only thing we have to do now is make sure that we put vector signs, because we are we're looking at things in 2 dimensions, right? So we have to use vectors. And if you're not familiar with vectors, or if you're uncomfortable with vectors, then it would be better if you could first watch those videos on vectors and then come back over here. So anyways, let's try.
Alright, guys, that's enough. Clearly explained that non-parallel problems. I think it was very clear. I don't have to add anything. Thank you very much. Remember, I was just giving the general introduction to the relative velocity. Hopefully now you have a clear idea of what is relative velocity. Yeah. Thank you very much.